All right, here we are with another problem, with an initial value problem now, with a first order linear differential equation system with an initial value. So, all right, we know that to solve this, we need to solve the, what's it called? The eigenvalue problem. So that's going to be 2 minus lambda, 4, negative 1, and 6 minus lambda. The vertical walls means the determinant, and that has to be equal to 0. Now, to find the determinant of this, I have to multiply this by this and subtract this by this. So let me do that. And I'm also going to factor out a negative sign from each term. So that will give me a lambda minus 2, and here a lambda minus 6. And then we have negative 1 times 4. Be careful there. Negative 1 times 4. And that's equal to 0. So here the first thing that we notice is that these two cancel out. And now we can develop this lambda squared. The sum of these two constant numbers is negative 8, and then we have that lambda because we're recognizing the pattern. Otherwise, you can multiply it normally and see that you'll get this. And then negative 6 times negative 2, that's going to be positive 12. And here we're going to have positive because the negatives cancel out, and 4 times 1 is 4. All of that is equal to 0. So we're going to have lambda squared minus 8 lambda plus 16 is equal to 0. Now, this is a perfect square. Lambda minus 4 squared is equal to 0. So I can take the square root on both sides, and I get, but I wouldn't do that. I would do this. Lambda minus 4 equals 0. So either lambda 1 is equal to 0 or lambda 2 is equal to 0. In either case, we have a repeated roots. Okay, so now that we know that we're dealing with the repeated roots, I meant to say 4 and 4, my bad. Because in order for the first term to be 0, lambda has to be 4. In order for the second term to be 0, lambda has to be 4. So once we do that, we can find the first vector easily. For lambda equals 4, what we can do is we can plug that lambda back in. So 2 minus 4, that's negative 2. 4, negative 1. 6 minus 4, that's 2. Okay. Can we get from this to this by multiplying by a single scalar? Well, if I divide by 2, yep, that works because negative 2 divided by 2 is negative 1, and 4 divided by 2 is indeed 2. Then here we're going to have our k components, k1 and k2. Remember, this comes from the eigenvalue problem. And now we can use just one of the two rows. So let's say negative 2 times k1 plus k4 times k2. All of that must be equal to 0. And so we can say that 4k2 is equal to 2k1, or that k2 is equal to 1/2 k1 if you divide both sides by 4. So let k1 be equal to 2, then k2 is going to be equal to 1, and we'd have the vector 2, 1 here for k1. Now, how do we find the second one? Well, this is kind of the tricky part. For the second one, so for this one, this came from the guess of x equals k e to the lambda t. Another guess that we can make is k times t e to the lambda t plus p e to the lambda t, where the lambdas are the same. But the k and the p are two vectors that are not the same. And then notice that there's this t here. So in this case, what do? Well, this is what we do. We end up having to also solve this system. So the same matrix, but now here we have P1 and P2, and that has to be equal to K. And if you're interested about the derivation of this, I encourage you to look at previous videos or to look at some other videos online. Okay. And K1 and K2, well, we found it. It's 2 and 1. So now we notice that these are also linearly dependent, the top row and the bottom row, because I can get to the top by dividing by the bottom by 2. So I'll just use the bottom. I get negative P1 plus 2P2 equals 1, or P1 is equal to 2P2. So let's say P2 is equal to 1, P1 is equal to 2. So now we can say that our P vector is 2, 1. Okay. Now, do you notice a problem here? I actually do notice a problem. That we already have 2, 1. We can't have the same vector. I wonder if we put it in MATLAB, or instead of putting it in MATLAB, if we substitute back in as it is, we're going to get an issue. We're going to get an identity, but we're not going to be able to extract any information out of this. So how do we do it if we don't want to input it into MATLAB? Well, let's say I say P negative P1. So again, I'm going to rewrite what I wrote before, equals 1. Or I can say P1, if I multiply everything by negative 1, minus 2P2 equals to negative 1. And so I can say that P2 is equal to 1. And then P1 will be equal, P1 minus 2 times 1 minus 1. P1 will be equal to negative 2, goes to the other side, becomes positive 2 minus 1. It becomes 1. So I think I made a mistake earlier. And now we have the vector 1, 1. So now, this is the tricky part. Our first solution only involves K. So it's going to be 2, 1. Remember, it came from this. So we're going to write this. I forgot to put the arrows on top of the vectors. And here we're going to have e to the lambda t. What is lambda? Well, lambda, we found out it's 4. So that's our first solution. But our second solution involves both k and p, so not just p. Because remember, it comes from this. So it's going to be k, which is 2, 1, multiplied by e to the 4t. Well, you're already forgetting something. We're forgetting the t here. T, e to the 4t. And then we have a plus. And again, we have a 1, 1 here. And then we multiply that by e to the 4 times t. And that's our second solution. So if we want to find the overall solution, we have to do a linear combination of the two solutions, which you do by multiplying each by a constant and adding them together. So the overall solution would be C1 times 2, 1, e to the 4t, plus C2 times, and again, here we have 2, 1, t, e to the 4 times t, plus 1, 1, e to the 4 t. And this, ladies and gentlemen, is our final answer. And if you were to verify this, you want to verify this, you'd put this in MATLAB probably, unless you want to write a lot, and take the derivative of it, and then set it equal to the matrix, the original matrix that we had over here at the top, multiplied by this answer, and see if the left-hand side is equal to the right. And if it is, you get bingo. Now, this is not the final answer. I was joking. We have the initial condition. So the initial condition is going to allow us to find the C1 and C2. And it's at x of 0. So that means when t is equal to 0, we get that vector, we get -1 and 6. So we get -1 and 6 here happens when we get C1. I'll distribute the C1, and so we get 2C1 and C1 times e to the 0, that's just 1, so I'm not even going to write it, plus C2, I'll distribute the C2, so we got, well, this whole term goes to 0 because it's t to the 0. Well, it's t at 0, and t is a multiple of this. Well, yeah, it is a multiple of this term. And then for the second term, we get e to the 0, so I don't write the e, I just need to write C2. Distribute it in, so C2 and C2. And then I can rewrite this in algebraic form. So that would be -1 and 6 and, well, before I rewrite it in algebraic form, I want to add those two vectors together on the right-hand side. So 2C1 plus C2 and C1 plus C2. And so we can say -1 is equal to 2C1 plus C2, and 6 is equal to C1 plus C2. Now, let's solve for C1 at the bottom. So C1 is equal to 6 minus C2. And I can plug it at the top. So -1 is equal to 2 times 6 minus C2 plus C2. So -1 is equal to 12 minus 2C2 plus C2. So -1 is equal to 12 minus C2, or C2 is equal to 13. Now, if I plug that back at the top, I get the C1 is equal to 6 minus 13, which is equal to -7. So these, assuming I didn't make some mistakes, should be our answers. So I can plug them back into C1 and C2 here, and I would get x is equal to C1, which is -7 times 1 e to the 4t, and then I have plus C2, which is 13, times that whole business, which is 1 t e to the 4t plus 1 e to the 4t. And now I'm not joking anymore. And this is indeed our final answer. All right, this was good. This was fun, and I can't wait to do the next one. So I'll see you next time. Bye.